In this experiment, I'm going to perform a Wittig reaction on an aldehyde called trans-cinnamaldehyde. That's this molecule right here. As you know, in the Wittig reaction, the oxygen of the carbonyl group is replaced by the alkyl group of the ylide, or the Wittig reagent. And the purpose of this experiment is to determine which isomer is formed in this reaction. Now, I do want to start off by saying that this particular reaction does not have any effect on the trans-alkene portion of cinnamaldehyde. That will not be changed. We're looking at the stereochemistry around the carbon-carbon double bond that is formed in the reaction. So when this portion is placed into this position on the molecule, will we make this particular stereoisomer where the hydrogens are on opposite sides of the double bond, or will we produce the other stereoisomer? These two isomers have really different melting points. So once we finish the reaction, we'll be able to get the melting point of the product and determine which one we made. This particular product over here, because the hydrogens are on opposite sides of each other on the double bond, this would be a trans double bond or an E double bond. And this one over here, because the hydrogens are on the same side of the double bond, this would be cis or Z. This particular isomer has a melting point of 88 degrees and the other has a melting point of 153 degrees. So pretty significant difference. It will be very easy to tell them apart. Let's watch the reaction. For this reaction, we're going to start with 1.3 grams of trans-cinnamaldehyde. I'm going to be putting it directly into a 50 milliliter Erlenmeyer flask. Cinnamaldehyde smells like cinnamon. .355 grams, and we also need to add, ooh, there's the cinnamon smell. We also need to add 3.9 grams of benzyl triphenyl phosphonium chloride. This is a solid, so I'm going to take this off and use a piece of weighing paper to measure out the benzyl triphenyl phosphonium chloride. This is a very fine powder. I'm going to try just pouring it. .116. This reaction is going to take place at room temperature. I'm using the hot plate only for the stirring function. I won't be adding any heat to this. So I'm going to get my stir bar going, even though there's barely anything in the flask at this point, just the cinnamaldehyde. Now I'm going to be adding my solvent. The solvent is dichloromethane, also known as methylene dichloride. And I'll need 10 milliliters of that solvent. Methylene dichloride is a pretty hazardous solvent, so I'm using my fingers just to stabilize the graduated cylinder, but once I start actually pouring, I'm going to move my fingers out of the way just in case I spill any of it. I don't even want to get it on my gloves. Normally, as you know, I'm pretty messy in the lab, but with something like dichloromethane, I try to be very careful. The next thing that I'm going to add is the ylide reagent, the benzyl triphenyl phosphonium chloride. There's a lot of it that needs to be added. So I'm pouring it in there slowly just to control it, just so I don't spill any of it. And the color change that you're seeing there is really just due to the addition of the white powder. The last thing that we need for this is 50% sodium hydroxide, which is a really high concentration for sodium hydroxide. And that I'll be using 5 milliliters. I am using the same graduated cylinder as I did for the methylene chloride, which is okay because it's all getting mixed together anyways. And then, like I said, this mixture is just going to stir at room temperature for at least a half an hour. Now this time when we're seeing a color change, this is an indication that a chemical reaction is definitely taking place. After this is done stirring, then we will begin the extraction process. The reaction period is over, and so now I'm just going to perform a simple extraction. This is just going to be a one-step extraction. This little Erlenmeyer flask contains our product, the methylene chloride solvent that was used for the reaction. There's a little bit of water in there because the sodium hydroxide was an aqueous solution. And then of course we have byproducts and things like that we want to get rid of. And our goal is just to simply extract the product. We're going to be using some dichloromethane, also known as methylene chloride or methylene dichloride. I use all of those names interchangeably, so maybe that's confusing. And what we're going to do here is just use 20 milliliters of the methylene chloride. Remember, this is the chemical that I'm nervous about. I don't like to spill it on myself, so I'm keeping both of my hands out of the way in case I spill it. Notice underneath my left hand, that little Erlenmeyer flask, that's the reaction flask, the flask that the reaction took place in. And look at how it's really hazy. That's because a lot of product is kind of trapped inside the flask, and we're trying to get the product transferred out of the flask into the separatory funnel. Now, unfortunately, I didn't quite have enough methylene chloride in that little bottle. It's empty. So that means I have to tap into this new bottle of methylene chloride. And I'm disappointed about that. It makes me sad because this is a brand new bottle, which means it's all the way full, and it's also quite a bit bigger than the other bottle. And both of those things make it really hard to pour. So it's pretty much impossible for me to pour this without spilling a little bit of it. And I really don't like to spill methylene chloride. But thankfully, I only needed a little bit. So I'm going to transfer the methylene chloride not into the separatory funnel, but I'm going to pour it into the Erlenmeyer flask. And as I pour it into the Erlenmeyer flask, I'm going to be rotating the Erlenmeyer flask so that the methylene chloride runs down all of the inside walls of this Erlenmeyer flask. And again, remember, my goal here is to try to get everything rinsed out of that Erlenmeyer flask and transferred into the separatory funnel. And then I'm going to repeat this with water. Do the same thing. I'm going to measure out a little bit of water, I think 15 milliliters. Transfer the water into the reaction Erlenmeyer flask, and then transfer all of that into the separatory funnel. Methylene chloride and water really do not mix with each other at all. This is one of the reasons why we don't have to repeat this extraction. It's going to be a really clean extraction. When I shake these two things up, they are going to form a little bit of what we call an emulsion, where it's kind of like what happens when you shake together a mixture of oil and water. So everything just, at least initially, the layers don't separate very well from each other, and you have to give it a little bit more time than normal to separate. What I'm doing right now with the shaking is mixing the methylene chloride and the water together. The product is soluble in methylene chloride, so all the product is going to transfer itself into the methylene chloride layer. And so now what I'm going to do is let this sit. Look at how it just is like one big hazy, cloudy layer. I'm just going to let this sit for probably about 5 minutes, so that the methylene chloride and the water layers can separate from each other. So now I have a really good separation of the layers. Unfortunately, the separation is right at the ring in the ring stand, so it's kind of hard to see, but as you can see, there's a littler layer on top. Methylene chloride is more dense than water, so it is the bottom layer of this mixture. So I'm draining the bottom layer out. The bottom layer, again, is the methylene chloride with our product. So it's the good layer, it's the layer that we want to keep. I'm going to drain this methylene chloride layer into the beaker because this is a layer that contains our product. I want to stop the draining process before the entire bottom layer has drained. I don't want to run the risk of getting any of the top layer into this beaker because I don't want to make the contents of the beaker impure. So I'm going to leave behind a little bit of the methylene chloride layer. And the last thing that needs to be done here, which is always what we do when we do an extraction with water, I need to use a little bit of drying agent, anhydrous sodium sulfate. This is that little white solid powder that we add. This will help to absorb any water that may have been trapped in the methylene chloride layer. Just adding the anhydrous sodium sulfate, swirling it around, and the anhydrous sodium sulfate clumps up when it absorbs water. So in this process, what we're doing is just sort of adding a couple of scoops, swirling, and observing the drying agent. It doesn't dissolve, so it's really difficult to see even in person, especially difficult to see on a video. What you're looking for are free-floating granules of the drying agent. So as I'm swirling it and I'm just kind of tilting the beaker to make it a little bit easier for me to see, and I'm just looking to see if I can see any grains of this floating around. If everything is clumped up, then that means that it's still actively absorbing water and that I need to add a little bit more. There isn't really ever any specific amount that you need to add. You just have to keep adding, swirling, and looking until you can finally see some granules that are no longer clumping. So now that I'm done with the drying agent, I'm going to transfer just the liquid into a clean Erlenmeyer flask. I don't want to transfer any of the drying agent, I just want to transfer the liquid. So I poured a little bit, but then also I'm using a pipette to transfer the rest. And in this process, it's impossible for you to transfer 100% of the solution. You're always going to have to leave a little bit of it behind. Once this has been transferred into the Erlenmeyer flask, I'm going to cover it up with plastic, poke some holes in the plastic, and just let the methylene dichloride solvent evaporate. And this is going to leave behind just the product of the reaction, which will hopefully be a solid. The flask has been sitting for a few days. All of the methylene chloride has evaporated. We have this yellow solid in the bottom of the flask. I'm adding a little bit of 60% ethanol. Take a look at the glass rod that I have in my right hand. It's got a flat bottom on it. I'm using the flat bottom of that glass rod to perform a technique called trituration. Trituration. It is literally just smooshing all of that solid into the 60% ethanol. The solid that's in our product is not soluble in 60% ethanol, so it's not going to dissolve, but it is possible that there are some impurities that might have gotten trapped in there with our product. And those impurities are going to be soluble in the 60% ethanol. So what I'm trying to do is just break up that yellow crystal chunk at the bottom of the flask, and hopefully I will dissolve any impurities in the 60% ethanol mixture. Once I feel like I've triturated it enough, smooshed it around enough, then I'm going to perform a filtration. I've got that filtering flask right behind me ready to go. That filtration process is going to catch all of the product because the product is not soluble in the 60% ethanol. And if there were any byproducts that were trapped in there, they have now been dissolved in the ethanol, and so they're going to pass through the filter funnel. This is not a purification process though. So after I do this filtration, I am still going to need to do a recrystallization. I am going to perform a recrystallization using 95% ethanol. This is the product that I filtered in the previous segment of the video. I'm going to transfer it into a beaker for recrystallization. The product, I literally just filtered it, so it's not dry. We're not taking a mass on it or anything. We're just going straight to the recrystallization process. And as I'm getting this transferred into the beaker, I also have on the hot plate that Erlenmeyer flask that contains some 95% ethanol that is heating up. I have a watch glass, that's that small, it kind of looks like a plate, watch glass sitting on top of the flask with the ethanol. And that is just simply because the ethanol evaporates pretty easily, and I don't want to lose it, I don't want to waste it. So I have the watch glass on top to minimize evaporation. So with the recrystallization, we want to start with some solvent inside the beaker that contains our product. We do not want to put the dry beaker directly down onto the hot plate because that makes it likely that we would burn or scorch our product. Too much heat. And in general with recrystallization, you don't usually know exactly how much solvent you need, so you just want to add a little bit of ethanol, swirl it around, stir it around. You have to wait for the ethanol to start boiling. So in my beaker, I have to be patient and wait for the ethanol to start to boil. Once the ethanol starts boiling, if I have undissolved product in the beaker, then that means I need to add more methanol and just repeat the process. So I'm going to add more methanol, stir it around, wait for it to start boiling, take a look if I can see any undissolved particles, add some more methanol, swirl it around, etc. This process can take a really long time because you just, don't really know how much ethanol you need to add. This has been chilling in ice for a little while. The products, the crystals are ready to filter, so I'm just going to transfer them into this filter funnel. Once everything has been filtered, then I'm going to allow it to sit and dry completely. That'll take a couple of days. And once it has been completely dried, then I will get a mass and we will measure the melting point. So now we're just going to get a mass on this product from our Wittig reaction. The product has been sitting and drying for about 4 days. And it's a really nice, flaky, shiny white. After getting this mass, then I'm going to take the melting point of the product so that we can determine which isomer it actually is. Looks like we got 0.573 grams. So we're going to be using the melting point to help determine which isomer, which stereoisomer we have for this Wittig product. The two isomers melt at, the first one melts at 88 degrees and then the second one melts at about 153. So right now it's at 85 degrees and we're gonna try the 88 degree melting point, and if we don't get anything melting at that temperature, then I'll heat it up to the next possible temperature. The machine is at 86 degrees and there is no sign of melting at all. So normally as we approach the melting point, things start kind of pulling away from the inside of the capillary tube, getting kind of sticky looking, and this doesn't look like it's changing at all. Now it's at 87 and no changes. It is now at 88 degrees and there's nothing going on inside that capillary tube. So what I'm going to do now is stop the machine and I'm going to have it very quickly jump up to the second possible melting point is 153. So I'm gonna have it really quickly jump up to, let's say, 149. You usually want to have it start at a temperature that's a few degrees below your expected melting point. And hopefully it doesn't melt on the way up to this 149 temperature. Right now you can see that it is starting to kind of look a little bit sticky in there. It's at 146 now. And it isn't actually, even though it might kind of look like it's melting, it's not actually melting, it's just really shrinking a lot. And I know, like, I can tell from the video it looks like it has melted, but it hasn't. That sort of reflective thing on the top there, that is a chunk of solid, and then on the bottom what kind of looks like a puddle, it's not a puddle, it's just another piece of solid that's dropped down to the bottom. But we're definitely very close to the melting point. There aren't any liquid droplets in there at all yet, so we're not at the actual melting point yet. So we're now at 149 and it does look like it is starting to melt. There is still solid there, so it's not done melting, but I would say the melting is going to start at 149. We've got that one little chunk left there in the upper right hand side that still needs to melt. 150 and it's still working on finishing melting. Got that one little speck at the top that needs to melt. looks like it's all done now. It's 151.